Welcome back to the Midnight Scientists. Close your eyes and let the world around you begin to soften at the edges. The sounds of the day, the distant hum of traffic, the ticking of a clock, the lingering thoughts of tasks left undone. Let them all dissolve into a gentle gray mist. Imagine you are standing in a high, open meadow, far from the lights of any city. The air here is cool, crisp, and carries the faint, sweet scent of damp earth and wild clover. Beneath your feet, the ground feels solid and eternal, and above you is the night. For a moment, just breathe with the universe. Inhale the stillness, exhale the noise. For most of our history, this was the limit of our world. We looked up and saw a velvet dome pinned with flickering diamonds. We imagined ourselves at the very heart of it all, a fixed, steady point around which the heavens performed a slow, majestic dance. In the 2nd century, Claudius Ptolemy sat beneath these same stars, mapping their movements with a quill and parchment. To him, the earth was a sanctuary, a heavy anchor in a sea of celestial spheres. He imagined the sun and the moon as guardians, circling us in perfect rhythmic arcs. Visualize that ancient universe. It was small. It was intimate. It was a home that had edges you could almost touch. There was a comfort in that stillness, the belief that we were the center of a grand, unchanging clockwork. But curiosity is a quiet fire. It begins with a single question, a single lens turned toward the dark. Shift your mind forward now, drifting through the centuries like a cloud across the moon. We find ourselves in the 1500s in the quiet study of Nicholas Copernicus. The air is thick with the scent of old paper and beeswax. He is looking at the planets, watching them wander across the sky, and he realizes that the dance is different than we thought. The Earth is not the anchor. We are the dancers. We are a marble of blue and green, caught in the golden pull of the sun. Feel the subtle shift in your perspective. The world is getting larger, but you are still safe. You are simply drifting into a wider sea. By the 18th century, William Herschel is in his garden, his giant telescope pointed upward like a silver finger. He is mapping the Milky Way, star by star, grain by grain. He sees a vast disc-shaped city of light. For a long time, we thought this city was the entire universe, an island of stars in an infinite empty ocean. We stood on the shore of our galaxy and looked out into the great beyond, seeing only a few fuzzy patches of light, like distant campfires in the fog. We called them nebulae. We thought they were mere clouds of gas drifting within our own borders. But the night had one more secret to tell, a secret that would stretch our hearts and our minds further than we ever thought possible. Imagine the year 1923. We are on the summit of Mount Wilson, California. The air is thin and cold, and the smell of pine needles is sharp in the breeze. Inside the great dome of the observatory, the 100-inch Hooker telescope sits in the darkness, a massive, silent titan made of iron and glass. Edwin Hubble is there. Can you hear the soft click of his boots on the metal floor? Can you see the faint red glow of his lantern? He is peering through the eyepiece, looking at a fuzzy patch of light in the constellation Andromeda. For nights on end, he watches. He is looking for a pulse. Deep within that smudge of light, there is a star a Cepheid variable. Visualize this star as a cosmic heartbeat. It doesn't shine with a steady light, it breathes. It grows brighter, then dimmer, brighter, then dimmer, a slow, rhythmic glow that follows a law discovered by Henrietta Leavitt. She was a woman who sat in a quiet room at Harvard, surrounded by thousands of photographic plates, finding the ruler of the universe in the flickering of the stars. She realized that the slower a star pulses, the brighter it truly is. By measuring the rhythm of this heartbeat in Andromeda, Hubble realizes something breathtaking. Andromeda is not a cloud in our galaxy. It is another galaxy entirely. It is 2 million light-years away. Imagine that distance. A light-year is the distance light travels in a single year, 6 trillion miles. Now multiply that by 2 million. The universe has just cracked open. It is no longer a small, intimate dome. It is a vast, echoing cathedral of islands. Thousands, millions, billions of island universes, each with its own suns, its own planets, its own stories, all drifting in the deep velvet dark. As you drift now, feel the weightlessness of this realization. You are no longer tethered to a small Earth. You are a passenger on a journey through an ocean that has no end. The stars are not just above you, they are all around you, stretching out into the infinite. But as Hubble looked closer, he noticed something even more mysterious. The galaxies weren't just sitting there, they were moving. They were moving away. Imagine a loaf of raisin bread dough sitting on a warm counter. As the dough rises, the raisins, our galaxies, move further and further apart. It isn't that the raisins are traveling through the dough, it's that the dough itself is stretching. Space itself is breathing. Space is growing. Since that moment in 1929, we have known that we live in an expanding universe. It is a beautiful, terrifying, and mesmerizing thought. Every moment, the distance between the stars grows a little wider. The universe is exhaling. But how fast is this exhale? That is the question that keeps the modern scientists awake in the quiet hours of the night. That is the heartbeat of the mystery we are about to explore. As you settle deeper into your pillows, let the image of the expanding dough fade. Replace it with the image of a calm, dark ocean. The ripples are moving outward, steady and sure. We thought we knew the speed of those ripples. We thought we had measured the tempo of the universe's breath. But the more we look, the more we realize that the universe has 2 different heartbeats, and they do not match. Is the universe truly what we think it is, or are we standing on the brink of a new way of seeing everything? Rest now in the mystery. The stars are pulsing. The dark is warm. The journey has only just begun. Take a slow, deep breath. Feel the air as it enters, cool and revitalizing, and as it leaves, carrying away the last remnants of the day's tension. You are drifting deeper now, moving from the simple realization that the universe is large into the mystery of how it moves. Imagine we are traveling away from the coastal fogs of California, moving inland and upward. The terrain changes, the air grows thinner, sharper, and the scent of the sea is replaced by the dry, sweet fragrance of ponderosa pines. We are in Flagstaff, Arizona, at the turn of the 20th century. Here, atop Mars Hill, sits the Lowell Observatory. Visualize the dome of the observatory resting like a silent white pearl against the ink-black desert sky. Inside, the world is hushed. There is no hum of computers here, no glow of digital screens. There is only the low, rhythmic ticking of a clockwork drive, a mechanical heartbeat that slowly turns the massive telescope to track the stars as the Earth rotates beneath it. In this quiet space, we find Vesto Slipher. He was a man born on a farm in Indiana, a person who understood the slow, patient cycles of the seasons. He brought that same patience to the stars. Between 1912 and 1925, while the world below was embroiled in the noise of history, Slipher sat in the cold, dark shadows of this dome. He wasn't just looking at the galaxies, he was listening to the light they emitted. Imagine light not just as a glow, but a message written in a secret code. Slipher used a spectrograph, a prism of exquisite glass, to catch the light from distant spiral nebulae and spread it out into a rainbow. Visualize that rainbow in your mind. See the deep, velvet violets on one end, bleeding into indigo, then a calm, cool blue. The colors transition into a soft green, a warm yellow, a vibrant orange, and finally a deep, resonant red. This is the spectrum of the universe. But within this rainbow, there are dark lines, thin black vertical marks like a barcode. These lines are the signatures of atoms, hydrogen, helium, calcium, the building blocks of all things. In a laboratory on Earth, these lines sit in very specific places. They are the fixed points of our reality. But as Slipher looked at the light from distant galaxies, he saw something haunting. The barcodes were not where they were supposed to be. Imagine you were holding a fine silk ribbon with markings on it. If you were to pull on the ends of that ribbon, stretching it out, the markings would grow further apart. The light from the galaxies was doing exactly this. Because the galaxies were moving away from us, the waves of light were being stretched as they traveled through the void. When a light wave stretches, it becomes longer, and in the language of color, a longer wave is a redder wave. Slipher watched as one by one, almost every galaxy he observed showed this red shift. It was as if the universe was a giant celestial choir, and every member was backing away from the stage, their voices dropping into a deeper, lower, ruddier pitch. Think of the sound of a distant train whistle. As it approaches, the sound is high and piercing, but as it passes you and disappears into the night, the pitch drops, a long, low, fading moan. This is the Doppler effect. Slipher was seeing the same thing, but with the very fabric of light itself. He found that these galaxies were racing away at incredible speeds, hundreds of kilometers every single second. But he didn't yet know how far away they were. He had the speed, but he lacked the map. While Slipher was at his telescope in the desert, another mind was working in the quiet cloisters of Europe. Georges Lemaitre was both a priest and a physicist, a man who saw no conflict between the soaring wonder of the spirit and the rigorous logic of the atom. Visualize him sitting in a dimly lit study, surrounded by stacks of mathematical equations. He was looking at Albert Einstein's new theory of general relativity, the idea that space and time are not a static stage, but a flexible fabric that can bend, warp, and stretch. Lemaitre realized something that even Einstein was hesitant to accept. If the equations were right, the universe could not be still. It had to be either shrinking or expanding. He imagined the universe not as an eternal, unchanging void, but something that had a beginning. He called it the primeval atom, a single, infinitely dense point of light and energy that began to unfold like a flower blooming in slow motion. At first, the world did not listen. The idea that the entire cosmos had a day without a yesterday was too strange, too revolutionary. Even Einstein told him, "Your calculations are correct, but your physics is abominable." But then, the farm boy from Indiana and the priest from Belgium were joined by the lawyer-turned-astronomer from California. Hubble took Slipher's measurements of speed and combined them with his own measurements of distance. He sat in the darkness of Mount Wilson, plotting points on a graph. Imagine a simple line rising steadily upward. On one axis is distance, on the other is speed. Hubble discovered a perfect poetic symmetry. The farther away a galaxy was, the faster it was racing away. If a galaxy was twice as far, it moved twice as fast. If it was 10 times as far, it moved 10 times as fast. This was the proof. The universe wasn't just moving, it was expanding in every direction at once. And if you were to play the movie of the universe backward, drifting back through the millions and billions of years, everything would come closer and closer together. The galaxies would overlap, the stars would merge, until everything, every atom in your body, every grain of sand on every beach, every star in every sky was tucked together in that single, silent, glowing point of the primeval atom, the Big Bang. As you breathe in the stillness of your room, try to visualize this expansion not as an explosion of noise and fire, but as a silent, majestic unfolding. Space itself is being created between the galaxies. The void is growing. The universe is a living, breathing thing, and we are caught in its slow, rhythmic exhale. We call the rate of this expansion the Hubble constant. It is the heartbeat of the cosmos. For decades, we thought we had measured this heartbeat perfectly. We thought we knew exactly how fast the universe was breathing. But as our telescopes grew more powerful, as we began to look not just at the stars, but at the very first light that ever existed, we found a discrepancy, a tension. The universe's heartbeat today seems to be faster than the heartbeat of its youth. Why would the breath of the cosmos change its tempo? Is there a hidden force, a dark energy, pushing the galaxies apart faster and faster? Or is our understanding of the very laws of physics, the legacy of Newton and Einstein, incomplete? Drift now into the deep blue of the evening. The galaxies are receding, the light is stretching, and the mystery is deepening. We have found the expansion, but we have lost the certainty of its speed. The night is long, and the secrets of the vacuum are waiting to be whispered. Allow your mind to drift even further back now.
beyond the galaxies, beyond the first stars, into a time when the universe was nothing but a warm golden haze. We are leaving the now behind, leaving the world of 73 kilometers per second and entering the realm of the deep past. To understand the heartbeat of the cosmos, we must look at its very first breath. Imagine you were standing in a thick, luminous fog. It isn't cold or damp. It is a fog of pure energy, a glowing plasma so dense and so hot that light itself cannot move through it. In this infant universe, just moments after the Big Bang, photons, the tiny particles of light, are like pinballs caught in a crowded machine. They strike electrons and protons, bouncing back and forth, trapped in a chaotic, brilliant dance. The universe is opaque. It is a sun that fills all space. But as the universe expands, it cools. Visualize the temperature dropping degree by degree over thousands of years. The frantic dance of the particles begins to slow. Around 380,000 years after the beginning, a mere blink in cosmic time, the temperature reaches a critical point. It is cool enough now for electrons to find their homes around protons, forming the very first atoms of hydrogen. This moment is called recombination, but you can think of it as the Great Clearing. Suddenly, the fog vanishes. The light that was trapped for eons is suddenly set free. It streams out in every direction, a flash of ancient radiance that fills the entire sky. This is the first light. It is the oldest thing you will ever see. But as this light traveled through the billions of years to reach us, the expansion of the universe did something remarkable to it. Just as the light from Hubble's galaxies was stretched into red, this first light was stretched even further. It moved past red, past infrared, until it became something invisible to our eyes: microwaves. This is the cosmic microwave background, or the CMB. It is the fossil of the Big Bang, a silent echo that resonates in every corner of the sky at every moment of every day. To find this echo, we don't go to a mountaintop in California. We go to a quiet, grassy hill in Holmdel, New Jersey in the year 1964. Imagine two scientists, Arno Penzias and Robert Wilson. They're working with a massive horn-shaped radio antenna originally built for satellite communications. It looks like a giant metal ear listening to the whispers of the heavens. But they have a problem. No matter which way they point the antenna, they hear a persistent low-level hiss, a static that will not go away. They think it's a flaw in the machine. They check the wires, they scrub the antenna, even removing a family of pigeons that had taken up residence inside. But the hiss remains. It is there during the day, it is there during the night. It is coming from the north, the south, the east, and the west. It is the sound of the universe's birth. They realize they are listening to the cooling embers of the Big Bang. That static is the light of the first clearing, stretched across 13 billion years of time and space. For this accidental discovery, they would later win the Nobel Prize, having touched the very hem of the beginning. Now, imagine we are fast-forwarding to the 21st century. We have moved beyond the simple hiss of a radio antenna. We have sent eyes into the deep cold of space. The WMAP satellite and the European Space Agency's Planck probe. These machines are designed to map that ancient light with exquisite, crystalline precision. Visualize the map they created. It isn't a picture of stars, it's a baby picture of the universe. It looks like a mottled sea of orange and blue, a tapestry of tiny fluctuations in temperature. Some spots are a fraction of a degree warmer, some spots are a fraction of a degree cooler. These tiny ripples are the seeds of everything. The warmer spots would eventually collapse under gravity to form the first clusters of galaxies. The cooler spots would become the vast, empty voids between them. Everything we see today, every galaxy, every black hole, every planet, began as a ripple in this ancient sea of light. But here is where the mystery deepens. Cosmologists can take that baby picture and apply the laws of physics. They can look at the size and the spacing of those ripples and rewind the clock, or rather fast forward it to the present day. They can calculate exactly how fast a universe with those ripples should be expanding today. And their answer is 67.4 kilometers per second per megaparsec. Remember our number from the first chapters. The measurements of the nearby universe, the one with the pulsing stars and the red-shifted galaxies, gave us a number around 73. 67.4 versus 73. In the world of everyday life, a difference of 5 or 6 seems small, but in the world of the cosmos, this is a chasm. It is like measuring the height of a child when they are a baby and predicting they will be 6 feet tall when they reach adulthood. Something happened. Either the child, the universe, grew faster than our models predicted, or there is a force at work that we do not understand. As you drift now, imagine the universe as a grand, ancient clock. One set of scientists is looking at the gears turning today, watching the hands move across the face. Another set of scientists is looking at the blueprint of the clock, drawn billions of years ago. The blueprint says the clock should tick at one speed, the hands are moving at another. Is the blueprint wrong, or is there a ghost in the machine? Visualize the silent, cold background of space, filled with that microwave glow. It is a blanket that covers you, ancient and warm. It has been traveling since the beginning of time just to reach this moment. It holds the secrets of our origin, but it also holds a riddle that challenges everything we thought we knew. The Hubble tension is not just a number on a chalkboard. It is a whisper from the deep past telling us that the story of the universe is far more complex and far more beautiful than we ever imagined. Sleep now in the light of the first dawn. The ripples are steady, the echo is calm. We are moving toward the heart of the crisis, but for now, we simply drift in the glow of the beginning. Let your breath become slow and rhythmic now, like the steady, gentle swell of a calm sea at midnight. We are moving away from the baby picture of the infant universe, away from the soft microwave glow of the beginning, and returning to the universe of today. We are going to look at how we measure the distance to the stars, not through blueprints and ancient echoes, but by building a bridge across the dark. Imagine a ladder. It is a ladder of light, and its feet are planted firmly here on our own rocky soil. Its top, however, vanishes into the deepest reaches of the velvet void, stretching across millions and billions of light years. Astronomers call this the cosmic distance ladder. Visualize the first rung of this ladder. It is built on simple, elegant geometry, the same logic a surveyor uses to measure the width of a river without ever crossing it. As the Earth orbits the Sun, our perspective on the nearby stars shifts just a tiny, tiny bit. If you hold your finger in front of your face and close one eye, then the other, your finger seems to jump against the background. This is parallax. Drift with me into the feeling of that movement. We are on a spinning marble, swinging in a great circle 150 million kilometers wide. By watching how a star wobbles against the more distant background, we can calculate its distance with the precision of a diamond cutter. But parallax only reaches so far. It is a short rung, a local reach. Beyond a few thousand light years, the wobble becomes too small to see, even for our greatest telescopes. To reach the next rung, we need a lighthouse. Imagine you are standing on a dark coastline, looking out over a black, tossing ocean. You see a light in the distance. Is it a small candle nearby or a massive bonfire miles away? Without knowing the true brightness of the light, you can never know how far it is. But what if every lighthouse was built to the exact same specification? What if every bulb emitted the exact same amount of energy? Then, simply by looking at how dim the light appears, you could calculate exactly how much ocean lies between you and the shore. In the language of science, we call these standard candles. Return your mind to the breathing stars of Henrietta Leavitt, the Cepheid variables. Visualize one of these stars now. It is a yellow supergiant, thousands of times more luminous than our own sun. It is not steady, it is a living, pulsing thing. It expands and cools, then contracts and heats up. In the silence of your imagination, see it glowing, fading, glowing, fading. Because of the work of Leavitt and Hubble, we know that the timing of that pulse tells us exactly how bright the star is. If it pulses once every 10 days, it has a specific wattage. If it pulses once every 50 days, it has another. By finding these stars in distant galaxies, we can step from our own Milky Way into the great beyond. They are the second rung of our ladder, the steady heartbeats that guide us across the first few millions of light years. But even the brightest Cepheid eventually fades into the background noise of a galaxy's light. To reach the farthest edges of the observable universe, to measure the expansion where it is fastest, we need something more powerful. We need a cataclysm. Imagine a pair of stars dancing in the dark. One is a normal star, much like our own sun. The other is a white dwarf, the tiny crystalline corpse of a star that has already lived its life. It is the size of the Earth, but has the mass of the Sun. It is unimaginably dense, a sphere of crushed carbon and oxygen. Visualize the white dwarf as a thief in the night. Its gravity is so intense that it begins to pull gas away from its companion star. The gas spirals down layer by layer onto the surface of the dwarf. The weight increases, the pressure builds. There is a law in physics called the Chandrasekhar limit. It states that a white dwarf can only weigh as much as 1.44 times the mass of our sun, not a grain more. The moment the thief steals enough gas to hit that limit, the entire star becomes unstable. In a fraction of a second, the white dwarf doesn't just collapse, it detonates. This is a Type 1a supernova. It is the most perfect explosion in the universe. Because they always explode at exactly the same mass, they always explode with exactly the same brightness. For a few weeks, a single dying star shines with the light of 5 billion suns. It becomes brighter than the entire galaxy that holds it. These are our ultimate standard candles.
They are the top rungs of the ladder. By spotting these rare, brilliant flashes in galaxies billions of light years away, we can see how much the light has been stretched by the expansion of space. Adam Rees and his colleagues have spent decades refining this ladder. They have used the Hubble telescope and now the James Webb telescope to look at these supernovae with a clarity that was once impossible. They have checked the rungs, they have tightened the bolts, they have measured the nearby universe's expansion over and over again. And every time they do, the answer comes back the same, 73. The late universe measurement, the one taken from the stars and explosions we can see with our own eyes, is fast, it is energetic, it is a universe that seems to be racing away from itself with a frantic hidden purpose. So here we sit in the quiet of the night, caught between two truths. One truth, written in the ancient microwave glow of the beginning, says the universe should be expanding at a stately, measured pace of 67. The other truth, written in the dying gasps of exploding stars, says it is racing at 73. If you were to walk from one end of a room to the other, and your left foot told you the room was 10 feet wide, while your right foot told you it was 11 feet wide, you would begin to wonder about the nature of the floor. Is space itself different than we thought? Is the dark energy that pushes the galaxies apart not a constant force, but something that changes, something that grows stronger as the universe ages? Or is there a dark radiation in the early universe that we haven't yet accounted for? Drift now into the image of that ladder, stretching up from your room into the infinite. Each rung is a star. Each step is a billion miles. We are climbing toward a mystery that might rewrite every textbook on Earth. The Hubble tension is the sound of the universe refusing to be simple. It is the sound of a secret waiting to be told. Feel the calm of the ladder. It is steady, it is bright, and even if it leads us to a place where our old maps no longer work, it is a journey made of light. As you settle deeper into the stillness, let your mind become as vast and as quiet as the space between the stars. We have seen the two heartbeats of the universe, the ancient echo of the beginning and the brilliant flares of the dying stars. We have felt the tension between them, the 5-kilometer gap that threatens to pull our maps apart. Now we must look at the force that governs it all. We must look at the invisible architecture of the night. Imagine you are drifting in the center of a great cosmic void. Here, there are no stars to guide you, no planets to ground you. There is only the deep violet-black vacuum. In the old world of science, we thought the vacuum was nothing. We thought it was an empty stage, a silent theater waiting for the actors, the atoms and the light to perform. But Einstein saw something else. He saw that space itself is a thing. It is a fabric. It is a presence. Visualize a vast silver web stretching out in every direction. This is the lambda cold dark matter model, the standard model of our universe. It is the recipe that describes how our cosmos grew from a hot, dense seed into the intricate garden of galaxies we see today. In this model, there is a constant struggle, a silent tug of war that has lasted for 13 billion years. On one side, there is dark matter. Imagine dark matter as the invisible scaffolding of the universe. It does not glow, it does not reflect, and it does not shadows. You could pass through a cloud of it and feel nothing but a ghostly chill. Yet it has weight, it has gravity. It acts like a cosmic glue, pulling gas and dust together to build the cities of stars. Without this invisible architect, the galaxies would simply fly apart, dissolving like smoke in the wind. Drift with me into the feeling of that pull. It is a heavy, comforting embrace. It is the force that wants to bring the universe back together, to keep it small and intimate. But there is another force, a phantom, a ghost in the vacuum. For a long time, scientists expected that the expansion of the universe would slowly grind to a halt. They thought that the gravity of all the stars and all the dark matter would eventually win the tug of war, perhaps even pulling the universe back into a big crunch. But the stars told a different story. Imagine two teams of astronomers watching those Type 1a supernovae, our standard candles, flicker in the deep distance. They expected to see the expansion slowing down. Instead, they found that the most distant explosions were much dimmer than they should have been. The galaxies weren't just moving away, they were accelerating. Visualize the universe as a car coasting down a highway. You expect it to slow down as it runs out of fuel, but instead, an invisible foot has slammed onto the accelerator. The car is moving faster and faster into the dark. We call this invisible foot dark energy. It is represented in Einstein's equations by the Greek letter lambda. Originally, Einstein called it his greatest mistake, a mathematical fudge factor he added to keep his universe static and still. But the universe, it seems, is never still. The mistake turned out to be the most dominant force in existence. Dark energy does not live in the stars or the planets. It lives in the space between them. As the universe expands and more space is created, there is more dark energy. And as there is more dark energy, the expansion happens even faster. Think of it as a silent tide that is rising bit by bit, pushing the islands of galaxies further and further away from each other. In the far, far future, this tide may grow so strong that every galaxy will be alone in its own private bubble of darkness, unable to see the light of its neighbors. But here is the heart of our mystery. Our standard model, this beautiful mix of dark matter and dark energy, works perfectly to explain almost everything we see. It explains the baby picture of the microwave background. It explains the way galaxies cluster together like glowing dew on a spider web. And yet, it cannot bridge the gap between 67 and 73. If dark energy is a constant, a steady, unchanging pressure of the vacuum, then the two numbers should match, but they don't. This suggests that the ghost in the vacuum might be more complex than we imagined. Perhaps dark energy is not a constant. Perhaps it is dynamic. Imagine the push of the vacuum changing over time. Perhaps it was weaker in the early universe, allowing the 67-kilometer heartbeat to set the pace. And perhaps as the eons passed, the dark energy evolved, growing stronger, more frantic, pushing the nearby galaxies at the 73-kilometer pace we see today. Or perhaps there is a dark radiation, a third invisible actor in the infant universe that we haven't yet accounted for. A hidden particle, a sterile neutrino,
or a ripple in the fabric of gravity itself that gave the early universe an extra kick. As you drift now, feel the mystery of the vacuum. It is not empty, it is brimming with potential. It is a living field that breathes and pushes and pulls. We are like sailors on a vast, dark ocean, trying to understand the currents that move us. We have the maps of the stars, and we have the maps of the beginning, but the water itself is changing beneath our feet. The Hubble tension is the universe's way of telling us that we are missing a chapter in the book of physics. It is an invitation to look closer at the nothingness of space. Visualize the silver web of the cosmos again. See the galaxies pulsing like fireflies, caught in a tide of invisible energy. It is a majestic, silent, and deeply peaceful sight. You are safe within this web. You are a part of the struggle and a part of the light. Rest in the unknown. The vacuum is not a void. It is a promise.
Take a moment now to find a position of perfect ease. Feel the weight of your body as it sinks into the surface beneath you, supported and safe. Imagine that the room around you is beginning to dissolve, the walls fading into a soft charcoal mist until there is nothing left but you and the vast, silent theater of the night. We have been dwelling on a mystery, a tension between two numbers. We have seen the universe through the eyes of the ancients, the pioneers of the telescope, and the modern satellites that map the whispers of the Big Bang. We have felt the confusion of the Hubble tension, where the early universe speaks of a slow, steady expansion, while the stars of today shout of a faster, more frantic race. But what if the answer is not found in a new particle or a changing force? What if the answer is something far more fundamental, something so simple that we almost missed it because we are already doing it ourselves? Imagine a child's spinning top balanced on a wooden floor. Visualize the top as it whirs, a blur of color and motion. To an ant standing on the edge of that top, the world is moving fast, the scenery is a streak of light. But to the ant at the very center, the world is much calmer. The motion is there, but it feels different. Movement is the one true constant of our existence. You may feel as though you are perfectly still right now, resting in the quiet of your room. But beneath you, the Earth is spinning on its axis at over 1,600 kilometers per hour at the equator. It is a dizzying, silent rotation that gives us our days and our nights. Visualize the Earth now, a marble of sapphire and cloud, turning in the deep dark. And the Earth is not alone in its dance. It is circling the sun, racing through the void at 107,000 kilometers per hour. The sun, in turn, is not a fixed point. It is orbiting the center of the Milky Way, dragging the entire solar system along with it in a grand, sweeping arc that takes 230 million years to complete. Everything we know is in a state of rotation. The planets spin, the stars rotate, and the galaxies themselves are massive, swirling whirlpools of light. But for a long time, we assumed that the all, the universe itself, was the one thing that did not turn. We imagined the universe as a static container, a vast, unmoving room in which the galaxies performed their dances. We thought the expansion was a simple, straight line, moving outward from the center like ripples in a pond. But in 2025, a group of thinkers, Zygoti, Zapuni, and their colleagues, proposed a radical, beautiful adjustment to our map. Imagine the entire universe is spinning. Drift with me into the idea of the universal rotation. It is not a fast spin. It is a slow, majestic, and nearly imperceptible movement. Their calculations suggest a rotation so languid that it takes 500 billion years for the cosmos to complete a single turn. To our human eyes, to our short-lived civilizations, it would look like perfect stillness. But on the scale of billions of light years, this spin changes everything. Think back to our two heartbeats, the 67 of the early universe and the 73 of the present day. When scientists introduce spin into their models, the tension begins to dissolve. Imagine you're on a carousel. If the carousel is perfectly still and you throw a ball to a friend on the other side, the path is a straight line. But if the carousel is spinning, even slowly, the path of the ball appears to curve. The motion of the carousel adds a hidden velocity to everything on it. The researchers realized that a rotating universe would affect the way light travels from distant galaxies. It would add a subtle shift to the redshift, making the expansion look faster in the nearby universe than it did in the ancient past. When they added this universal spin to the equations, the two numbers, the 67 and the 73, began to align. The tension wasn't a crisis of broken physics. It was the result of us standing on a moving floor and assuming it was still. There is a deep poetic comfort in this idea. Ancient Greek philosophers like Heraclitus said, "Panta rei," everything flows, nothing stands still. To think that the universe itself is part of this grand rotating flow connects us to the very largest scales of reality. Visualize the cosmos not as an exploding balloon, but as a vast, rotating ocean of space-time. The galaxies are not just flying away, they are drifting in a gentle cosmic current. This theory is new, and scientists are still testing its boundaries, running simulations and checking the maps. It may be the missing piece we have been searching for, or it may be another step towards an even deeper truth. But it reminds us that the universe is never done surprising us. As you drift now, feel the subtle imaginary pull of that great rotation. You are part of the spin. You are part of the dance. From the atoms in your cells to the farthest quasars at the edge of the dark, everything is moving in a rhythmic, balanced, and eternal cycle. Is the universe a closed loop? Is it a spiral that never ends? The carousel is turning, the stars are wheeling overhead, and you are safe in the center of the motion, cradled by the laws of physics and the beauty of the unknown. Rest in the turn. The night is revolving. The dream is just beginning.
Let your mind drift now to the edge of a great, quiet sea. You are walking along a shoreline that seems to stretch forever in either direction. The sand beneath your feet is cool and fine, like powdered starlight. The waves lap against the shore with a rhythmic, pulsing hiss, the breath of the ocean, steady and ancient. As you look out over the water, the horizon is a clean, sharp line where the deep indigo of the sea meets the pale violet of the twilight sky. In our everyday lives, we are used to things that have a beginning and an end. We walk from one room to another. We finish a book. We watch the sun set, knowing it will rise again. Our world is defined by boundaries, by fences and walls, by the limits of our own sight. But tonight, we are going to contemplate the word that has haunted mathematicians and dreamers for thousands of years: infinity. Visualize the number line. Start at 1, then 2, then 3. In your mind, try to find the biggest number possible. Imagine a number so large it fills the entire sky, a number with a billion zeros trailing behind it like the tail of a comet. Now, imagine adding 1.
There is always another one. There is always another step. In mathematics, infinity is not a destination, it is a direction. It is the realization that the path never truly ends. But what does this mean for the universe? What does it mean for the space that holds the stars? If you were to step into a craft capable of traveling faster than a beam of light, a vessel that could glide through the vacuum for 1,000 years, then 1,000,000, then 1,000,000,000, what would you find? Would you eventually come to a wall, a great shimmering barrier that marks the end of everything? Or would you simply find more space, more stars, more galaxies drifting in the velvet dark? Drift with me into the first possibility, the flat universe. Imagine a vast, infinite tabletop that stretches out in every direction forever and ever. If you were to draw a grid on this table, perfectly straight lines crossing each other at right angles, those lines would stay parallel for eternity. They would never touch. They would never curve. They would simply go on across the reaches of time, through the hearts of 1,000,000,000,000 galaxies, never deviating by even a hair's breadth. This is the universe as we often perceive it. When we look at the stars, they seem to sit in a space that is straight and true. When we point a telescope at a distant quasar, the light seems to travel to us in a direct, unbending path. To our human senses, the universe feels flat. In a flat, infinite universe, the possibilities are staggering. If space goes on forever and the laws of physics are the same everywhere, then eventually the patterns of matter must repeat. Imagine a deck of cards. There are only so many ways you can shuffle them before you get the same hand twice. In an infinite universe, there are only so many ways you can arrange atoms before you get the same star, the same planet, perhaps even the same you, sitting in a room very much like this one, looking up at a sky that is identical to ours. It is a thought that is both beautiful and bewildering, an infinite sea of worlds where every story that can happen does happen somewhere across the endless shoreline. But is the universe truly a flat tabletop? Astronomers have spent decades trying to measure the flatness of space. They look at the cosmic microwave background, that baby picture of the first light, and they measure the size of the ripples. If the universe were curved, those ripples would look slightly distorted, like a face seen in a funhouse mirror. But our measurements come back with startling precision. The universe appears to be flat to within a margin of less than 1%. Yet there is a catch. Think of the Earth. If you stand in the middle of a vast desert, the ground looks perfectly flat. You can see the horizon, and it looks like a straight line. You could walk for miles and believe you are on a flat plain. It is only when you climb high enough into the thinning air of the upper atmosphere that you see the subtle, majestic curve of the world. Perhaps our universe is like that. Perhaps it is so incredibly vast that even the parts we can see, the billions of light years reachable by our telescopes, are just a tiny, tiny patch of a much larger structure. Imagine we're like ants on the surface of a balloon the size of a sun. To us, every step feels like a straight line. Every grid we draw feels perfectly flat. We are too small to see the curve that connects the beginning to the end. As you drift now, feel the scale of this thought. You are resting on a tiny point within a vastness that may have no edge. The straight lines of your room, the straight lines of your thoughts, they are all part of a geometry that is deeper and more mysterious than we can fathom. Is the universe a tabletop that goes on forever? Or is it a shape that eventually loops back on itself, a grand cosmic circle that we are just beginning to map. The ocean is quiet, the horizon is calling, and the grid of reality is waiting to be traced. Rest in the vastness. The shoreline is infinite, but you are home.
Take a breath, slow and steady, and feel the gentle curve of your own breath as it cycles within you. We have explored the flat, endless tabletop of a universe that stretches into infinity. But now, let us drift into a different kind of mystery. Let us imagine that the lines of the universe are not straight, but possessed of a gentle, inevitable grace. Imagine you are a traveler in a vast, dark forest. You pick a direction, a single star to guide you, and you begin to walk. You believe you are traveling in a perfectly straight line, moving further and further away from the campfire you left behind. But as the hours turn into days and the days into years, you notice a familiar glow ahead of you through the trees. You step into a clearing and find your own campfire, still smoldering. You have traveled in a circle without ever turning. You have found the end where the beginning was waiting. This is the beauty of a spherical universe. Visualize the grid of reality again, but this time, instead of a flat sheet of paper, imagine the grid is drawn onto the surface of a great shimmering bubble. In this universe, there is no such thing as a truly parallel line. If you and a friend were to start at the equator of this cosmic sphere, standing miles apart and both walking perfectly straight toward the north, you would eventually find yourselves walking toward each other. You would meet at the pole. In a spherical universe, space is finite, but it has no edge. Think of the old computer games where your character walks off the right side of the screen only to instantly appear on the left. It is a world that loops, a world that is closed upon itself. In such a place, light itself would perform a grand, sweeping orbit. If you had a telescope powerful enough, and if the universe were still enough, you could point it into the dark, and after billions of years, see the back of your own head. You would be looking at the light that left your own body, traveled the entire circumference of the cosmos, and returned home. Drift with me into the comfort of this loop. There is a safety in a universe that contains everything within a grand celestial embrace. It is a finite house with infinite rooms, where you can wander forever and never be truly lost, for every path eventually leads back to the heart. But why would space curve? The answer lies in the heavy, silent presence of mass. Imagine a trampoline pulled tight and flat. If you place a heavy bowling ball in the center, the fabric stretches and sinks. If you roll a marble across the trampoline, it no longer moves in a straight line. It follows the curve of the fabric. Einstein taught us that gravity is not a force that pulls from a distance. It is the warping of the fabric itself. We see this most clearly in the most extreme places in the cosmos, near the hearts of black holes. Visualize a black hole as a tear in the velvet of space. Around its equator, there is often a ring of glowing gas spinning at nearly the speed of light. But when we look at a black hole, we see something strange. We see the ring not just around the middle, but arching over the top and beneath the bottom. This is a beautiful illusion. There are no rings on the top or bottom. What you are seeing is the light from the back of the ring being caught by the intense gravity and bent around the sphere of the black hole toward your eyes. The gravity is so strong that it has turned space into a lens, showing you the front and the back of reality at the same time. If enough mass exists in the entire universe, if the dark matter we spoke of is heavy enough, it could pull the entire fabric of the cosmos into this grand internal curve. But there is one more shape, a shape that is harder to visualize, but perhaps the most haunting of all. Imagine a saddle, the kind a rider uses on a horse. This is the hyperbolic universe. In a hyperbolic universe, space curves outward instead of inward. If you and your friend were to start walking parallel to each other here, you would not stay the same distance apart, and you would certainly never meet. Instead, you would drift away from each other at an ever-increasing rate. The lines of the grid would diverge, spreading out like the petals of a flower that never stops blooming. In a hyperbolic universe, space is truly infinite, and it grows more infinite the further you go. For every mile you travel, there is more than a mile's worth of new space waiting for you. It is a world of endless branching paths, a place where the darkness is always widening, always opening new doors into the unknown. As you drift now, consider the mystery of our own home. When we look out at the distant galaxies, we see them all moving away from us. We see them diverging, just as they would in a hyperbolic world. Is it because of the shape of space itself? Is the universe naturally open, destined to spread out until every star is a lonely island in a sea of nothingness? Or is the mass of the galaxies pulling us back toward the flat, steady ground? The scientists look at the maps and they see a universe that appears flat, but perhaps it is like a calm lake on a still night. To the eye, it is a perfect mirror, but beneath the surface, there are currents and curves we cannot see. Perhaps the universe is all three, hyperbolic in its nature, curved in its details, and flat in its balance. Sleep now and let your mind explore these geometries. Imagine your thoughts as lines of light, curving through the dark, meeting and diverging, forming a grand invisible tapestry. You are the traveler, you are the campfire, and you are the star. The loop is closing, the divergence is beginning, and the shape of the night is as deep as a dream. Let your thoughts drift like slow-moving clouds across a moonlit sky. We have traveled through the geometry of space, through the loops of spheres, and the endless stretches of flat horizons. Now we must turn our gaze back to the when. We must look at the clock of the cosmos and ask if the hands are moving in the order we once believed. Imagine you have a new pair of eyes made of gold and beryllium, capable of seeing the heat of a distant fire through a wall of smoke. These are the eyes of the James Webb Space Telescope. In late 2021, we sent this massive golden mirror into the deep cold of space, a million miles away from the warmth of the Earth. Its mission was simple but profound: to peer back through time, across billions of light years, to see the very first stars igniting in the dark. We expected to see a sparse, quiet time, a proto-universe where matter was only just beginning to huddle together into small, fragile clumps. We expected to find the toddlers of galaxies, tiny and dim. But when the first images returned, the silence of the observatories was replaced by a collective gasp of wonder and confusion. The early universe was not a quiet nursery.
It was a bustling, brilliant city. Visualize the deepest reaches of time, 13 billion years ago. Webb saw galaxies that were far too large, far too bright, and far too mature for their age. It was as if you had looked into a preschool and found it filled with fully grown adults in business suits. According to our models, there simply hadn't been enough time for gravity to pull so much gas and dust together to form these massive structures. Cosmology is in crisis, some began to whisper. Had we gotten the age of the universe wrong? Was the Big Bang not the beginning we thought it was? But as the scientists sat with the data, breathing through the shock, they began to find the ghosts in the light. Imagine one of those too bright galaxies. It looks like a fuzzy red dot at the edge of the mirror's vision. To make a galaxy that bright, you would need billions of stars. But what if the light wasn't coming from stars at all? Deep in the heart of these early galaxies, there were monsters. Visualize a supermassive black hole. It is a place where space is squeezed so tightly that it vanishes. But it is not the black hole itself that shines. It is its meal. As the black hole pulls in the surrounding gas, the gas begins to swirl in a frantic, glowing whirlpool called an accretion disk. The friction is so intense, the energy so concentrated, that this single point can outshine all the stars in the galaxy combined. By accounting for these hungry leviathans, the crisis began to soften. The galaxies weren't too big, they were simply too hungry. The black holes were acting like spotlights, making small galaxies appear much more massive than they truly were. Everything seemed to fall back into line with the 13.8 billion-year-old clock. Except for one thing. The black holes themselves were still too big. Think about how a black hole is usually born. A massive star lives its life, runs out of fuel, and collapses in a violent supernova. What is left behind is a stellar black hole, about 10 or 20 times the mass of our Sun. To become a supermassive black hole, millions of times the mass of the Sun, it has to eat. And eating takes time. There is a law in the universe called the Eddington limit. Imagine you are trying to fill a narrow-necked bottle with water, but the water is also boiling and steam is rushing out. If you pour too fast, the steam will push the water back out of the funnel. Light works the same way. As a black hole eats, it glows. That light carries momentum, a tiny physical push. If a black hole eats too much too fast, its own brightness will push its food away into the void. The Eddington limit is the universe's way of saying, slow down, you can only grow so fast. But Webb saw black holes that had reached the size of giants in a fraction of the time allowed by this law. It was as if a baby had grown to the size of a mountain in a single afternoon. How did they bypass the limit? Did they skip the star step entirely? Imagine a universe so dense, so filled with gas, that the clouds didn't wait to become stars. Instead, they collapsed directly under their own weight, thousands of suns worth of matter falling into a single point at once. These are direct collapse black holes. They were born as giants. Or perhaps they found a way to cheat the light. Visualize a black hole called LID 568. Webb watched as this distant object consumed matter at 40 times the Eddington limit. It was super-accreting, snatching at the gas so quickly that the light didn't have time to push it away. It was a cosmic glutton, breaking the rules of physics just to exist. As you drift now, feel the awe of these impossible objects. We are learning that the early universe was a place of wild, rule-breaking energy. It was a time of giants and gluttons, a time when the laws we see today were being tested and pushed to their breaking points. The eyes are shining in the dark, the giants are growing in the silence,
and the clock of the cosmos is ticking with a rhythm we are only just beginning to hear. Rest in the light of the first fires. The impossible is happening, and you are here to see it.
Take a long, slow breath and let the quiet of the room settle over you like a warm, heavy blanket. We have looked into the hearts of the first galaxies, and we have seen the giants that dwell there. We have witnessed the impossible growth of black holes that seem to defy the very laws of light. Now we must move closer. We must drift toward the edge of these leviathans, not to see how they destroy, but to see how they might, one day, save us. Imagine you were a tiny speck of light drifting toward the silhouette of a spinning black hole. For a long time, we thought of black holes as cosmic drains, silent, cold, and absolute. We believed they were the end of the story, a place where information and energy went to die. But as we look closer at their features, we realize they are more like the engines of the universe. They are the most efficient batteries in existence. Visualize the black hole in front of you. It is not a solid object. It is a region of space where gravity has won every battle. Around it sits the event horizon, that famous invisible sphere of no return. But because this black hole is spinning, it has created a second, even more mysterious zone just outside the horizon. This is the ergosphere. Drift with me into this strange, swirling territory. Here, space itself is no longer still. Imagine you are standing on a moving walkway in a vast airport, but the walkway is moving at nearly the speed of light. Because the black hole is rotating with such immense mass, it drags the fabric of reality along with it. This is frame dragging. In the ergosphere, you cannot stand still. Even if you fired the most powerful rockets in the universe in the opposite direction, you would still be swept along in the whirlpool of space-time. Reality here is a carousel that cannot be fought. But within this whirlpool lies a secret of nearly infinite power. In the 1960s, a mathematician named Roger Penrose sat with his equations and realized something breathtaking. If you were to send a vessel into this spinning ergosphere and have it split in two, dropping one half into the black hole while the other half escaped, the half that escaped would come out with more energy than it started with. It would have stolen a tiny bit of the black hole's rotation. Visualize this Penrose process. It is like a cosmic slingshot. By dipping into the edge of the abyss and pushing off against the spinning fabric of space, we could harness the kinetic energy of 1 billion suns. A single spinning black hole could power an entire civilization for trillions of years. It is the ultimate source of green energy, the energy of gravity itself, clean, eternal, and vast. But the ergosphere offers us something even more profound than power. It offers us a loophole in the laws of speed. Einstein told us that nothing can travel faster than the speed of light. This is the universal speed limit, and it is the reason the stars feel so far away. Even at light speed, it would take us years to reach our nearest neighbors and eons to cross the galaxy. But remember what is happening in the ergosphere. Space itself is moving. Think of a surfer on a wave. The surfer isn't swimming through the water at incredible speeds. The water itself is moving, carrying the surfer along.
Frame dragging shows us that space-time is flexible. It can be stretched, it can be twisted, and it can be moved. If we could find a way to manipulate the fabric of space the way a spinning black hole does, if we could create a bubble of space that moves while we sit still inside it, we wouldn't be breaking the speed limit. We would be riding the road itself. This is the dream of the warp drive. It is the idea that we don't need to go faster than light. We just need to make the universe move for us. As you drift now, feel the thrill of this possibility. The black holes we once feared as destroyers are actually our teachers. They are showing us that the rules of the universe are not walls, they are textures. They are showing us that space is not a vacuum of nothingness, but a fluid that can be harnessed, a sea that can be sailed. The Hubble tension and the impossible galaxies all point to this same truth. Our understanding of space-time is still in its infancy. We are like children looking at the waves on the shore, unaware of the deep currents and the tides that move the entire ocean. Visualize yourself now, safe and weightless, drifting at the edge of the ergosphere. The light of the accretion disk is a soft, golden halo. The spin of the universe is a gentle hum in your bones. You are at the edge of the infinite, and the path to the stars is opening, not through brute force, but through the elegant dance of geometry and grace. Sleep now in the engine room of the cosmos. The power is steady. The way is clear. The voyage is only just beginning.
Take a slow, deep breath, feeling the air expand your chest before releasing it into the quiet of the night. We have stood at the edge of the spinning abyss, glimpsing the power that lies in the curvature of space. But now we must step back to look at the grandest architecture of all, the sprawling web-like structure of the universe itself. Imagine you are a giant, standing so tall that whole galaxies look like tiny flickering embers at your feet. From this height, the universe does not look like a chaotic mess of stars. It looks like a delicate, glowing tapestry, a cosmic web. Visualize the threads of this web. They are long, shimmering filaments made of gas and dark matter stretching across hundreds of millions of light years. Where these threads cross, they form great knots of light, the superclusters. This is where the galaxies huddle together for warmth in the dark. Our own home, the Milky Way, lives on the edge of one of these threads, part of a vast celestial neighborhood called Laniakea. In the center of Laniakea, there is a mystery known as the Great Attractor. It is a heavy, silent point that pulls us toward it with the strength of a quadrillion suns. We are drifting toward it now, at 1,000,000 miles an hour, sliding down the curvature of space like a marble toward the center of a bowl. But in 2017, astronomers realized that something was missing from our maps. We are moving toward the Great Attractor, yes, but we are moving much faster than its gravity alone should allow. It was as if we were being pulled by a magnet, but someone was also giving us a firm, steady push from behind. Drift with me now, away from the crowded cities of stars, into the great empty spaces between the filaments. Imagine a region of space where there is nothing. No stars, no gas, no glowing dust, just a vast, lonely bubble of pure vacuum, 100 million light years across. This is the dipole repeller. For a long time, we thought gravity only pulled. We thought to move you had to be attracted to something heavy. But the dipole repeller taught us the power of the void. Think of a crowded room. If everyone huddles together in one corner, the other side of the room becomes empty. If you are standing in the middle, you feel the pull of the crowd, but you also feel the absence of the empty space behind you. In the universe, nothing can be just as influential as something. Because the dipole repeller is a void, it has less gravity than the surrounding filaments. In the grand tug-of-war of the cosmos, the regions with matter are pulling on us, while the void has simply let go of the rope. As a result, we fall away from the void and toward the matter. It is a push created by the absence of a pull. Visualize our galaxy, the Milky Way, caught in this cosmic slipstream. Behind us is the great silent emptiness of the repeller, nudging us forward. Ahead of us are the glowing towers of the Shapley supercluster, calling us home. We are moving through the dark, balanced between the void and the light. There is a profound peace in this motion. It reminds us that even the empty spaces in our lives have a purpose. The nothing is not just a lack of things. It is a force that shapes our direction. It is the silence that allows the music to be heard. As you drift now, feel the scale of this cosmic journey. You are not just sitting in a room on a planet. You are part of a grand intergalactic flow moving across the shores of eternity, guided by the unseen hands of gravity and the quiet whispers of the vacuum. The web is vast and the voids are deep, but the path is set. You are moving with the tide of the universe, and the tide is gentle. Let your breathing become as effortless as the starlight traveling through the deep. We have looked at the great voids that push us and the superclusters that pull us, but now we must shrink our perspective. We must travel from the gargantuan down to the infinitesimal. We must leave the realm of galaxies and enter the shimmering, uncertain world of the quantum. Imagine you are a weaver, sitting at a loom that stretches across the entire universe. The threads you are working with are not made of silk or wool, but of information. In our world, the world of trees and chairs and the steady beat of your own heart, we believe in the law of before and after. We believe that the past is a locked room, the present is the doorway, and the future is a path we haven't yet walked. We believe that for one thing to affect another, they must touch, or at least whisker across the distance at the speed of light. But as we peel back the layers of reality, down past the atoms, down to the subatomic particles that make up your very soul, we find that the weaver has a different set of rules. Visualize two tiny particles born from the same flash of energy. They are entangled. This is not a metaphor, it is a physical bond that defies everything we thought we knew about space. You could take one of these particles and leave it here on your bedside table and take its partner to the very edge of the dipole repeller, billions of light years away. If you were to reach out and tickle the particle here, changing its spin, making it dance, the particle on the other side of the universe would dance at the exact same instant. Not a second later, not a millionth of a second later. Instantly. Einstein called this spooky action at a distance. He hated it. He felt it broke the universe's speed limit. But the universe doesn't care about our limits. It seems that on the loom of the quantum, distance is an illusion. The two particles are still somehow the same thing. They are two needles sharing a single thread. Drift with me into the strangest part of this mystery. In 2006, scientists performed an experiment called the delayed choice test. They sent a photon, a single particle of light, toward a fork in the road.
the photon had to choose path A or path B. Under normal circumstances, if we don't watch the photon, it acts like a wave traveling down both paths at once, interfering with itself like ripples in a pond. But if we place a detector to see which path it took, the photon decides to be a particle and picks just one. But here is the twist that will make your mind feel like it is floating in a dream. The scientists waited until the photon had already passed the fork. Only then did they decide whether or not to look at it. And somehow, the photon in the past knew what the scientist would choose in the future. If they chose to look, the photon retroactively picked a single path. If they chose to stay in the dark, the photon retroactively traveled through both. The future changed the past. The weaver reached back and re-wove the thread that had already been laid. As you drift now, settle into the profound, quiet implication of this truth. Perhaps time is not a one-way street. Perhaps the universe is not a series of falling dominoes, but a finished tapestry that we are only experiencing one stitch at a time. Could the Hubble tension, that mismatch between the beginning of the universe and the now, be a result of this quantum ghost? Could the future of the cosmos be reaching back to influence its birth? Is the expansion of space a conversation between the end and the beginning? The scientists call it retrocausality. You can call it the memory of the future. Visualize your own life as part of this shimmering web. Your tomorrow is already connected to your yesterday. You are not just a passenger on a timeline, you are the tapestry itself, vast, interconnected, and eternal. The particles are dancing, the threads are vibrating, and the clock is not a line, but a circle of light. Sleep now in the heart of the quantum. The past is safe, the future is waiting, and the weaver is at rest.
Let your consciousness drift into the deep, indigo quiet of a world without weight. We have traveled from the first sparks of the Big Bang to the edges of the spinning abyss. We have seen the push of the void and the strange backward whispers of the quantum. Now we come to the final horizon. We come to the question that settles over the soul like the first snow of winter. Where does it all go? Imagine you were sitting on the moon of a distant, lonely planet at the very end of time. The sky above you is no longer crowded with the brilliant overlapping light of 100 billion galaxies. The expansion we have tracked, that steady, rhythmic breath of the cosmos, has continued for trillions of years. Visualize the great unraveling. Because of dark energy, the ghost in the vacuum we spoke of earlier, the islands of light have drifted so far apart that their light can no longer reach each other. One by one, the neighboring galaxies have slipped beyond the horizon of the observable universe, vanishing into the permanent dark. The stars in your own sky are growing old. They have burned their hydrogen, pulsed their last red glow, and faded into cold, dark cinders. The great nebulae, the nurseries of light, have all been used up. The universe is becoming a vast, quiet gallery of ghosts. This is what some call the heat death. It sounds cold and perhaps a bit lonely, but drift with me into the peace of it. In this state, the universe has reached its final equilibrium. There are no more fires to burn, no more shadows to cast. It is a state of perfect crystalline stillness. The tension we have spent our journey exploring, the mismatch of numbers, the struggle of forces, has finally been resolved into a single, eternal note of silence. But is this truly the end? Or is the universe a more patient storyteller than that? Recall the universal rotation we discussed, the idea that the entire cosmos is slowly, majestically turning. If the universe spins, then perhaps it does not just expand and fade. Perhaps it breathes. Visualize a cyclic universe. Imagine that the expansion we see today is just the inhale. Perhaps billions of years from now, the spin or the hidden geometry of space will cause the tide to turn. The expansion will slow, then stop, and the universe will begin its long, slow exhale. The galaxies will begin to drift back toward each other. The voids will shrink. The light will begin to turn from red back to blue. In this vision, the Big Bang was not the beginning, but a big bounce. The moment a previous universe finished its exhale and began a new life. Think of the Hubble tension one last time. That 5-kilometer difference between the baby picture and the grown-up universe. Perhaps it isn't a mistake. Perhaps it is the momentum of the previous cycle still rippling through the current one. It is the lingering heartbeat of what came before, whispering to what is here now. As you drift now, feel the deep, rhythmic comfort of this cycle. You are not a traveler on a road that leads to a cliff. You are a passenger on a grand, celestial carousel. The darkness is not a grave, it is a womb. The silence is not an end, it is the pause between breaths. Everything you are, the atoms of your body, the sparks of your thoughts, have been here before, in a different form, in a different light. And you will be here again. You are part of the Panta Rai, the eternal flow that never stands still, yet never truly leaves. Visualize the entire tapestry of the cosmos, from the first light to the final cinder, as a single, glowing loop. It is a shape of perfect beauty, a geometry of total grace. The midnight scientists are not just those who look through telescopes. They are the ones who can sit in the dark and feel the pulse of the infinite. They are the ones who know that the mystery is the home and the search is the destination. Close your eyes now, truly. Let the numbers fade. Let the tension dissolve. The universe is expanding, and you are expanding with it. The universe is turning, and you are cradled in the turn. The light of 13 billion years is washing over you, and it is as warm as a summer sun. Rest in the heart of the crisis that turned out to be a song. Sleep. The stars are watching. The void is holding you. And the dream is infinite.